And we're back. Welcome back and happy Tuesday. Today we're going to switch gears and finish up our final module, namely on the Central Limit Theorem. Now this is an important theorem in probability, and we will use it as a way to express arbitrary distributions in the form of a standard normal so that we can draw comparisons. Before we go over this, let's go through a few administrative bits. So the reading by the 24th of November in the Barron text, pages 89 through 95, covering sections 4.2.4 to sections 4.3. Including today, we have 3 classes left. Some key dates. Residence halls will close this Wednesday, the 25th, during which time, at 5 p.m., you will vacate the campus, only to return in the spring semester if you are residential. Last day of classes is the 3rd of December. Reading day is the day after, 4th. The scheduled final exam period for this class will be Tuesday, the 8th of December, in the block of time from 10:30 in the morning till 12:30 in the afternoon, during which we'll have final project presentations. The last day of finals will be the 11th of December, at which time you will be submitting your final projects. That will be at 8 p.m. Please make sure you have noted these key dates. So when we last left off, we talked about the normal distribution, and we said the normal distribution is a good descriptor for stochasticity concerning inertial quantities, things that you measure in the physical world and the natural world, such as pressure, position, velocity, temperature, and so forth. And so because it is a continuous or real valued, uncountably infinite quantity that we're trafficking in with a normal distribution, we say it has a probability density function. And there's our density f of x is 1 upon radical 2 pi sigma squared, e to the minus 1 over 2 sigma squared times x minus mu quantity squared. Last time we spoke about and proved the law of total probability. And then we proved the expectation as well as the variance. Okay, so let's take a look at the so-called standard normal distribution. And so we have our normal distribution, and this normal distribution is parameterized by the location parameter mu, the mean, and the scale parameter sigma squared, the variance, square root of which is standard deviation. And we said the mean is the center or location of that distribution, and the standard deviation is the dispersion associated with this distribution. And for the dispersion, we said that the bigger our standard deviation and therefore variance, the more spread out our probability mass was for this density. And the smaller the standard deviation and therefore the variance, the more concentrated this density probability mass is for this density function. And so what happens when we change the mean mu, our location parameter? Well, here's our distribution, and we have it centered about the mean mu. And if we change it, well, one thing we could do is set mu equal to 0. Now, if we set mu equal to 0, something interesting happens. Well, the center of our distribution is about the origin, 0, but the shape of the distribution does not change. We still maintain our standard deviation sigma above and below the mean. And so all we've done, and I'll just sort of toggle back and forth, all we've done is just shifted the location of our normal distribution. So let's make our mu 0, therefore centering our distribution. And in practice, what we can do to center that distribution is we take each one of our measurements, x1, x2, x3, and so forth, all big N, many of them, and we subtract from each of those measurements the mean. So the new version of x1 is going to be x1 minus mu. The new version of x2 is going to be, therefore, x2 minus mu, and so forth. The new version of xn is going to be x big N minus mu. Okay, so that is changing the location. One thing we can also do when we center it about origin is we can also change our standard deviation. So what happens when we change it? Well, let's think about this. So let's divide each one of our measurements, x1, x2, and so forth, up to and including xn. Let's divide everything by our standard deviation. Of course, we can achieve that by multiplying by 1 over sigma. So we take x1 and we divide by sigma, take x2 and we divide by sigma, up to including xn, and we divide by sigma. What happens there? Well, if we divide by sigma, these values are getting smaller. They're being pulled in closer to one another. Some values that are closer to 0 are smaller in magnitude. Those values that are further away from our mean are larger in value. And so by dividing everything by sigma, we're moving all the points in, or measurements x, in towards the origin if it's centered about origin. Otherwise, we're moving them closer in to the mean if it's centered about a mean that's non-zero. In doing so, essentially what happens is we sort of concentrate our standard deviation. We make it smaller by dividing by standard deviation, and therefore those values are drawn in and it becomes less dispersed. And it becomes less dispersed in a particularly interesting way when we divide all the measurements by the standard deviation. The variance becomes unit, or variance becomes 1. If our standard deviation becomes 1, well, the variance is nothing more than standard deviation squared, so therefore the variance becomes 1. And so these two transformations, this shifting to origin by subtracting off the mean, and this scrunching in towards the origin by dividing by the standard deviation, this changes our mean mu to be 0. That's the centering process. And then this dividing by sigma, our standard deviation, each of these measurements, that changes our variance to be a unit variance, a variance of 1. And so when we do this, it's no longer a normal distribution. It's called a standard normal distribution, or so-called z-distribution. And a z-distribution is nothing more than a normal distribution that has a mean of 0, mu is equal to 0, it's centered, and the variance is of unit variance. Sigma squared is equal to 1. Now, of course, you can take each of your measurements for your random variables, the first measurement x1, second measurement x2, and so forth, up including the nth measurement, and we can get an equivalent so-called score, z-score, or z-value associated with each point. It's the new version of our measurement after we've done this transformation of centering by subtracting off the mean and scrunching it in, standardizing the variance. And so the corresponding z-score associated with each input, you take the input x, you subtract off the mean, that's centering it, this distribution about origin, and then you divide by the standard deviation. So then if we did a little bit of algebra here, well, we multiply both sides of equality by sigma, and then we add mu to both sides of equality, and we get the following expression. Our value x, which is our original measurement, is mu, the mean, plus sigma times this z value, this z-score. And so there's this relationship when we perform these transformations that we can transform a normal distribution into a z-distribution, our so-called standard normal distribution. Okay, and so if we look at the standard normal distribution, we said it's the same as the normal with mu equals 0 and sigma squared equals 1. So of course, we'll set sigma squared equal to 1 here, and mu is equal to 0. And if we do so, our density function changes. It's 1 upon radical 2 pi e to the minus x squared upon 2 sigma squared. And therefore, for the cumulative distribution function, or CDF, we take our density and we integrate from minus infinity to x of our standard normal density dx. So this is our standard normal distribution. Now you might be wondering, why in the world should you care about this? Why is this important? Well, let's think about what percentages did for proportions. Now, if we said we had a value of, say, 100, and that value increased to 150, we could also talk about another example where we had a value of 50, and it increased to a value of 75. Now, of course, in the first case, we said our increase was a total of 50 units increase. Second case, our increase was a total of 25 units of increase. Now, of course, the scale is different for these. And if we express these in terms of percentages per centum per 100, we say this increased by 50%, 50 per 100. And we also say in the second case, this increased by 50%, 50 per 100, that common rate. And so by standardizing to a single system of measurements per 100, this percentage, we're now able to make a comparison between these two. And that becomes particularly important for the following cases. So suppose we said we had 100 and we increased to 125, and then we had 50 and we increased to 75. Now, of course, the amount of the increase is 25 in the first case and 25 in the second case. But the rate of increase for the second case is much larger. That represents 50% per 100 per centum. The first case represents only 25%. So by casting these two problems along the same scale of measurement per 100, we can make a fair comparison and then say, okay, well, the second scenario had a larger increase than the first scenario, even though the amount of the increase was the same. So thinking about what percentages did for proportions, with the standard normal distribution, we can take all of our normal distributions, cast them into the standard normal distribution through this transformation. The z is the same as the x measurements minus the mean over the standard deviation. We can now cast them in a standardized way. And that's exactly what the standard normal or z distribution does. It allows you to cast your normal distributions along the same scale of measurement so that now you can make fair comparisons or make statements about them. Okay, so suppose we have a series of temperatures. Temperature is uncountably infinite. It's an inertial quantity from a physical system and is therefore well described. The stochasticity in this measurement is well described by a normal distribution. So suppose we have temperature x, and it is governed by a normal distribution with some mean mu, or average temperature, and some variance sigma squared, the variance in the temperature. Now this is for a certain geographic location. So we standardize it, and now with the standardization, if we have temperatures from two different geographic locations, we standardize it, and now we can make comparisons between the temperatures for these two locations because they're now expressed all along the same scale. So we can say things like which locale had a more variation in its temperature, which was more dispersed, which one on average was warmer, was cooler, and so forth. What was the difference between the coldest and the warmest, and so forth. So now we can make fair comparisons in the same way that percentages allow us to make fair comparisons along the same scale of measurement for proportions. Okay, so this is why the standard normal distribution is so important. Let's follow with Central Limit Theorem to kind of bring everything on home. Now, we said the standard normal allows you to take two normal distributions, scale them the right way so that they're making fair comparisons. You can make a fair comparison between them. Now, of course, there are more distributions than just the normal. And so the Central Limit Theorem is that final piece that we need that allows you to transform any distributions we've studied, transform them to be an equivalent normal distribution. So given those two things, now, if you have a non-normal distribution, you use the Central Limit Theorem to transform it to a normal distribution, and then you convert it through transformations to the standard normal, and now you can compare, for example, the variability in a Poisson with the variability for a binomial, for example. All right, so let's consider any random variable. You have some random variables distributed as some distribution, and that distribution has a set of parameters. We talked about lambda for the Poisson, we talked about lambda for the geometric, we talked about alpha and lambda for the gamma distribution, we talked about the mean, mu, and sigma squared for the normal distribution. Now, numerous operations that we can make on measurements involve the sum of some number of observed outcomes. Now, this mirrors the discussion in the book, and so we're going to call Sn the sum of n many measurements. The first measurement we're going to call random variable x1, and the nth measurement we're going to call random variable xn. So if you have some operations, and these operations are of this form where it involves a sum, we can take advantage of the central limit theorem. So let's see an example of this. So when we computed the average, we said the average is the same as the expectation under the assumption of equiprobable outcomes, uniform events. And so when we compute this average, we take our sum, x1 plus x2 plus x3 up to including xn, and we're going to multiply that sum by 1 upon n. So this is just some scalar a, where a in this case is equal to 1 over n. So it's just some scalar a times that sum Sn. And that's exactly what our average is. So the average, it is a transformation that involves a sum. And so let's take a look at the variance and expectation of this transformation of this sum, this calculation involving a sum. So we have our sum Sn, and if we were to take the variance of Sn, well, we expand out what Sn is. That's the variance of x1 plus ... to xn. Now, of course, we know the property of the variance is such that the variance of the sum is the sum of the variances. So that's equal to the variance of x1 plus the variance of x2 ... plus the variance of xn. So if we do that, of course, we know the variance of that variable we said is just sigma squared. So we have sigma squared plus sigma squared added to itself n many times. And so that's just n times sigma squared. And so that's the variance of our transformation involving the sum. Of course, we're dropping the scalar for this consideration. We can do the same thing with the expectation of this sum, this function, this transformation involving a sum. So if we do that, of course, the expectation of Sn is the same as the expectation of x1 plus x2 ... plus xn, little a. And so expectation has linearity property as well. Expectation of the sum is the same as the sum of the expectation. So that's just the expectation of x1 plus the expectation of x2 plus ... the expectation of xn. Well, the expectation of a variable we said is mu. So that's mu plus mu ... plus mu. We're going to add mu with itself n many times, and that's just going to give us n times mu. And so n mu is the expectation of the sum. And if we have a really large number of measurements involved in this sum, well, n gets really, really big. And if we were to think of the distribution of what this sum is, well, the variance goes to infinity, and so too does expectation go to infinity. So as a distribution here, the variance or the distribution of this transformation involving this sum, that new quantity, the distribution of that, it diverges. It's infinite. It has infinite variance and infinite expectation. So let's think about what happens when you take the average involving this sum. So we're going to divide by n. So we have the variance of Sn divided by n. We're taking the average. That's just the variance of Sn over n squared. Anytime you have the scalar times something, you take the variance. That scalar is squared. So we have the variance of Sn over n squared. Now, again, we said from before the variance of Sn is n times sigma squared. So we have n times sigma squared. And this gives us the result. Cancel n in the numerator with a copy of n in the denominator. This gives you a result of sigma squared upon n. We can do similarly with the expectation. The expectation of Sn over n is, well, expectation is just n times the expectation of each one. That's n times mu. So we have n times mu over n, copy of n in the numerator and denominator. That's just mu. And so when we have this average, okay, something interesting happens with the statistic. So here we have this quantity now is an average. And when we take that average, when n gets really big, well, what happens? That variance gets smaller and smaller and smaller. It goes to 0. Now, a variance of 0 is a distribution where we have a single value where all of the probability of that value equals 1, all the probability is at a single point called a point mass. And so when we take this average, the variance as n gets really big becomes a point mass, a zero variance, and the expectation is just mu. So we have a finite expectation, and we have a variance going to 0. Okay, so let's think about somewhat of a variation. Let's take the quote-unquote root average instead of the average. So we're going to divide by radical n. So if we take our sum, transformation, we divide by radical n and take the variance of this resulting root average, as I'll call it. Well, we square that scalar, so that becomes variance of Sn over n, because the radical n squared is just n. And then from before, we have the variance of Sn is just n times sigma squared. We have a copy of n in the numerator and denominator, that's just sigma squared. For the expectation, we take expectation of the same quantity, Sn, our root average divided by radical n. Well, in the numerator, that's just n times mu, which is n times the expectation of the variable, divided by radical n. And so if we do that, well, n in the numerator is the same as saying radical n times radical n. So I have a copy of radical n in the numerator and denominator, and that's just radical n times mu. And so this particular root average in an infinite number of measurements involving our sum, this behaves just like a distribution. This transformation, Sn divided by radical n. We see that its variance has a non-zero value. It's defined, it's not infinite either. And the expectation is just some scaling of mu. It has an actual finite expectation. So this behaves just like a distribution. It has a dispersion, and it has an expectation, radical n times mu. And so, in fact, it behaves just like a so-called standard normal distribution. So let's get to the crux of today and look at the standard normal. So let's define a set of independent and identically distributed random variables. So that's how we represent a number of samples from the same distribution. They're independent, meaning that one sample doesn't affect the other, and they're identically distributed, meaning that they have the same distribution. And so if you have each one of these measurements from the same distribution, and it has a finite expectation for each of those xi's and a finite variance that's defined, then if you normalize the statistic involving a sum, then this distribution is going to converge to look like a standard normal. So let's think about what that means. So if we redefine our distribution to involve some function that includes a sum, if that sum is big enough, it'll look like a standard normal. So here, we're going to standardize it. We said to standardize, we take our value and we subtract the expectation and we divide by its standard deviation. So here is our z transformation, and we have our sum, Sn. We're going to subtract from it its expectation, and we're going to divide that result by the standard deviation. So if we do that, that's just Sn minus the expectation of Sn over square root of the variance, because standard deviation is square root of the variance. And so from before, we have the expectation of Sn is n times mu. So we have Sn minus n times mu in the numerator. And in the denominator, we have the variance. The variance, we said, was sigma squared n. We take the square root of that. That's sigma times radical n in the denominator. And so this z-score for the sum is going to be a standard normal. And this is the transformed version of the quantity that we get when we compute the original sum over our observations. Okay, and so this is our standardization procedure. And what the central limit theorem tells us, that it doesn't matter what that distribution is for the original variable. If we have that sum involve enough terms, then the resulting standardized version of this Sn quantity involving the sum is going to have a shape of a distribution that is going to be a standard normal. And this means that then we can take a Poisson, We can take a geometric, we take a gamma distribution, and we can turn it into a standard normal distribution, which we can then use to compare the stochasticity of, for example, a Poisson to a geometric. All right. And so why is central limit theorem a big deal? What the big deal is, and this is the main takeaway from today, is that it doesn't matter what form your distribution takes, what form the stochasticity is. It could be in time, like a Poisson. It could be the number of trials until a success, a string of failures ending in a success. As long as you have a large enough set of observations, your n goes to infinity, you can compute a transformation on it to make it behave like a normal distribution, specifically, if you standardize it, a standard normal distribution. So what this means is that you have a single or standard way in which to make comparisons between the stochasticity of one system and the stochasticity of another. Absolutely beautiful theory. Okay, so I've taken liberty to write a MATLAB program to show you the power of the central limit theorem. So we start out and we sample from a Poisson distribution some number of times, and we have parameter lambda, and we have our number of samples in each case is 10,000 samples, and we plot a histogram of those individual distributions. So here are our Poisson samples. We do the same thing for a binomial distribution with probability P of heads equals 30% or 0.3. Number of binomial trials is 1,000. We sample from that binomial, and then we plot it. We do the same thing for a geometric distribution. Our geometric distribution's probability of success is 25%, 0.25. We sample some number of samples many times. Number of samples is equal to 10,000. We also sample from our uniform distribution. A is 1 and B is 100. We have number of samples, 10,000. We plot a histogram. Then we sample from our exponential distribution. Lambda is 10. We sample that 10,000. And then we also have a gamma distribution, alpha. The number of phases is 5, and lambda is 10. We sample that 10,000 times. We also have our normal distribution, mu. The mean is 5. Sigma, the standard deviation, is 20. So sigma squared is going to be 400. We sample from the normal distribution. We compute a histogram. So then, to show what happens with the central limit theorem, we sample from our distributions again. And this time, instead of computing the individual measurement, we're going to compute the mean or the average of these measurements. So we take our samples for each one, Poisson, 10,000 of them, 500 trials, number of times we're going to do this. We take the mean of our Poisson samples. We do that 500 times. We compute the histogram. We do the same thing for the binomial. For the geometric, we take the geometric samples, 10,000 of them, we add them together. We do that 500 times. We compute the histogram. And we do that again for the uniform. And we do that again for the exponential. We do that for the gamma. And then we do that, of course, for the normal distribution. So in the interest of time, I have the outputs of those graphs. Figure 1 here, that's the original distribution. Let me blow that up so it's easier to see. Here we have the Poisson distribution. Here we have the binomial distribution. We have the geometric distribution. You see that exponential decay. We have the uniform. It's almost straight across, plus or minus some variation. We have the exponential. We have the gamma distribution. And then lastly, we have the normal distribution. That's figure 1. Figure 2 are those same distributions. Now, instead, we're plotting the mean of these. Here is the Poisson. You can see it looks like a normal distribution. Here is the binomial. It looks like a normal distribution. Here is the geometric. It looks like a normal distribution. Here is the uniform. It looks like a normal distribution. Exponential, it's a normal distribution of point mass. The gamma, normal distribution is the point mass. And the normal distribution is the point mass. And so we've taken these distributions that look very different, and we're now converting them to a normal by just plotting the histograms of that sum of samples versus the samples themselves. So this is just to show you that the central limit theorem really does work. And if I had standardized them, subtract off the mean from each measurement, the mean of these means, and divided by the standard deviation, we'd get them all centered about origin and with a unit variance. Okay, so with that, let's end here. I'll meet you back in the. So that's all I had to say, and we'll end there and finishing up our module on all of the distribution things we had to say for the semester. Again, please make sure you're staying up on these key dates and the reading. And as usual, please stay healthy, please stay safe, have a great Thanksgiving, and safe journey home. I will see you all on Tuesday. Happy Thanksgiving.